precision in science, medicine, mathematics, and the arts, both a means and an end in the service of mankind, symbolized best perhaps by one of man's most valuable servants, the timepiece. From the beginning of civilization, the accurate measurement of time proved one of man's most formidable and elusive challenges. Men met this challenge, but it took generations of dedicated craftsmen to do it, to develop timepieces accurate within seconds a day. The finest timepiece, the chronometer, is a marvel of precision in miniature. Weighing only a fraction of a pound and housing scores of moving parts, it will run accurately within seconds a year. Today's skilled craftsmen are applying the same spirit of dedication in meeting a modern challenge, manufacturing generating equipment to produce electric power for the needs of our nation and the world. To meet this modern challenge, we build a marvel of precision in magnitude, the Powermaker. Men have demonstrated their ability to craft precision timepieces to meet human needs. This is the story of man's ability to meet the challenge of precision on a giant scale. The story of large steam turbine generators built like a 700-ton watch, only better. This is the General Electric Large Steam Turbine Generator Department in Schenectady, the heart of America's electrical industry, the beginning of experience in turbine generator design and production, the birthplace of Powermakers. It occupies about 2 million square feet of modern manufacturing facility, enough space to accommodate 30 football fields. These men build turbine generators and assemble them. These men are the strength of the large steam turbine generator department, the experience. Like master watchmakers, many have spent their lives at their trade. They are unsurpassed as craftsmen in their field. Precision requires men like these, and they in turn need good tools, and the department has them in every size and variety. In contrast to the relatively modest investment required for watchmakers' tools, this Ingersoll planer miller represents an investment of $1.25 million. But it is capable of machining turbine high-pressure shells in approximately 1/3 the time formerly required and with greater accuracy. This Betz horizontal boring bar is also a major machine tool investment, and it provides significant savings both in the cost and time of the finished boring of turbine outer shells. The Betz engine lathe represents another major investment and another time saver in the machining of turbine rotors. This special lathe cuts grooves to hold turbine buckets on the wheel and does it in 1/3 the time required by previous methods. Just as precision is vital to the performance of a chronometer, it is vital in the performance of a 700-ton large steam turbine generator, but far more difficult to achieve. From the contour milling of an 80-pound turbine bucket to the slotting of a 140-ton generator rotor, precision must be maintained to tolerances within thousandths of an inch. Only this emphasis on precision by the pound or by the ton can assure years of uninterrupted performance of rotor speeds of 1,800, 3,000, or 3,600 revolutions per minute. Through years of experience, General Electric has developed a unique quality control program that ensures levels of turbine generator precision and operation far superior to the finest chronometer ever built. A part of this program is component testing, supported by applied research and development in materials and processes, and research in advanced manufacturing techniques. The General Electric Component Test Program covers all major phases of manufacture and assembly. During manufacture, component parts are individually tested and adjusted under normal and overspeed conditions to assure accuracy of design and manufacture. The assembly phase of the General Electric component test program provides the guarantee that when parts are assembled, they will operate perfectly by fitting, aligning, and adjusting mating parts under precise and controlled conditions. General Electric proves that before a turbine generator unit is shipped, it is functionally perfect as well as mechanically perfect. To demonstrate, let's follow one production cycle and see how component testing guides General Electric in the building of these precision power makers. Designing and building a steam turbine generator is both a science and an art, and there is no mass production in this business. Each unit must be designed and built to meet specific electric utility requirements. This takes 1.5 to 3 years, depending upon complexity and kilowatt rating of the power maker. After turbine generator designs have been completed and approved, patterns of major castings are made. Metal poured, and shells cast. Then machined to within thousandths of an inch of final form. Modern machine tools, some the largest and most advanced of their type, handle the biggest machining jobs. This Ingersoll milling machine is the largest of its kind in the world. On the table, a turbine outer shell casting for a 350,000 kilowatt unit. This monster machine tool does the work of 3 18-foot planers and has room for a second setup while the first is in process. Welded steel fabricated parts are also machined to within thousandths of an inch on this planer. X-ray and ultrasonic tests probe for hidden gas pockets and impurities at the start of and during the manufacturing cycle. For the most minute flaws can, under years of high temperature operation, affect the reliability of the unit. Typical of the thorough nature of the component test procedure is that designed for the turbine front standard, the nerve center of the unit, regulators, governors, controls, and emergency operating equipment. At the regulator test area, initial pressure regulators are operationally checked with high pressure oil and the linkage exercised for proper operation. Steam seal regulators, vacuum trips, intercept valve relays, and other critical devices are also checked and adjusted at this test station. At the valve test facility, all valves for each turbine are assembled and test run as complete components. All aspects of valve operation, including possible stem binding, friction, and oil leakage, are carefully measured to verify proper function. All operating governors are assembled, and components are checked individually for interference, friction, and operational point setting. After a successful test series, component parts are disassembled for additional alignment and friction checks, then reassembled, rechecked, and made ready for shipment. Emergency governors are installed on their stub shafts and run at rated speed and overspeed to assure proper operation under actual service conditions. The end result, a front standard, precision built to provide years of dependable service. From front standard to turbine, a 200-ton engine with a 50-ton drive shaft or rotor. This new grooving lathe can peel metal from a 100-ton rotor forging at a rate in excess of 30 pounds per minute, with grooves up to 2.5 inches wide. The recent development and use of super tough 12 chrome alloy in turbine rotor forgings increases rotor strength by 25% over conventional materials and will make possible a higher kilowatt capacity range. This is ticklish work. The slightest mishap, a bad cut, a gouge, and tens of thousands of dollars worth of material and man-hours lost. This man knows it. That's why he's the best in his craft. He has to be. Another master craftsman operates this Cincinnati Gilbert horizontal boring machine. Using the General Electric Mark Century tape control, this machine can bore flange coupling holes accurate to 1/1000th of an inch in diameter and location. The ability to machine to these precision tolerances permits final assembly without line boring. This man makes 6 precision parts at once, with the aid of a 6-spindle Cincinnati bucket miller. This modern machine contour mills 6 turbine buckets simultaneously with a cutter movement that traces the form of a master bucket. Optimum bucket contour is a matter of thousandths of an inch, and a series of special tests help assure that General Electric steam turbine buckets will perform with maximum design efficiency. This contour test measures the complex profile of modern turbine buckets to assure operation at specified design efficiencies. Resonant frequency tests assure that individual buckets are within specific tolerances of vibration frequencies. Magnetic, sonic, radiographic, and visual tests verify that finished buckets contain no imperfections that might cause eventual service failure. Finally, spectroscopic tests confirm that each bucket is made of the specified grade of alloy steel. A typical steam turbine rotor assembly will contain from 2,000 to 6,000 buckets of various shapes and sizes. Locking these finished buckets onto turbine wheels and wheels onto rotor pave the way for the dynamic balance test to determine the amount and angle of weight changes necessary to produce perfect dynamic rotor balance. A built-in computer helps accomplish this job, and the balance must be perfect. But when installed, a 50-ton rotor will spin at 3,600 revolutions per minute, with bucket tips traveling faster than a speeding bullet. The next major step in the turbine component test program is an analysis of rotor balance and overspeed performance. From this facility, General Electric gains more accurate vibration data than can be obtained from a rotor actually operating in an assembled turbine, and can in turn make extremely sensitive balance corrections. In the assembly phase of component tests, turbine erection tests are conducted to assure that all major components and internal parts fit with specified packing, wheel, and diaphragm clearances. From front standard and turbine to generator, the production source of electric power. Generator rotor forgings for a typical modern unit can tip the scale at 140 tons. This slotter can cut a 2-inch groove in a 25-foot forging in 4 hours. Each groove requires 3 passes. For the total job, 30 days to complete a generator rotor slotting. Generator rotor windings receive high potential tests at twice the rated line-to-line voltage plus 1,000 volts. Generator rotor balancing leads to the correction of unbalances along the entire length of the rotor, while high potential tests at 1 to 10 times the rated voltage determine and evaluate dielectric characteristics. And where necessary, we go vertical to bore generator stators and make a 3-to-1 reduction in the floor space required to do this operation. The taping of stator bars, once a slow and laborious hand operation, is now fast, efficient, and of much improved quality. Thanks to the recent installation of this unique stator bar taping machine designed and built by General Electric's large steam turbine generator department. This job once required 8 men, 8 strong men, but no more. A new carrier takes most of the strain out of this operation and makes possible faster and better generator stator bar installation. After each stator bar is secured in place, the stator rotates in position to bring the next slot into line. The exciter is the 4th vital component of a large steam turbine generator and it too receives a series of electrical and mechanical performance tests. After the tests, disassembly and inspection, then adjustment and partial reassembly for shipment to the utility customer. And 700 tons of precision power maker is created. 1½ to 3 years in the design and building, the product of experience, research and development, investment and precision. Precision on a giant scale at Schenectady General Electric. Precision through quality control and component testing to meet the rigorous levels of efficiency and dependability needed by today's electric utilities. This is the story of precision power makers, large steam turbine generators that must be built like a 700-ton watch, only better.